Hello everyone, hope you're doing fine. Uh, I will describe the paper Many-to-Many Symbolic Multitrack Music Gen Transfer. For this paper, I counted with the help of Dr. Hector Perez Miana, Dr. Toru Nakashka, and Dr. Mariko Nakano, and myself, Master in Science, Michel Pesat. So, in simple terms, what we want to do is, let's say we have a piece of music which is in a certain genre, and we want to achieve a cover of the same piece of music but in any other different genre. Humans, of course, can do this by having musical knowledge and experience, but we want to see if we can count with computers that can achieve the same task. So, to mention some related work, the most important ones, or the most that are similar to the one that is presented here. First is this a universal music translation network, which is based on the WaveNet network for generating audio in a raw format. The achievement of this proposal is of high quality, but is not as fast due to the sample-by-sample generated procedure. On the other hand, we have the symbolic approach, which use the MIDI format. In this case, we can mention the variational autoencoder, and the one that we gonna be discussing here is the generative adversarial network, which is similar to our approach. So the general adversarial network is basically a deep generative network which builds a probability distribution of certain data, and by doing so it uses a generator and discriminator. The generator will create new data similar to the data that was trained with, and the discriminator will evaluate whether this data is a real sample or it was generated by the generator network. So as we can see here in this image, we have the generator network and the discriminator network. We can say that this is a sample generated by this network and conditioned by this input, and the discriminator will evaluate whether these samples that are taken as input are real or fake. In order to train the generator network, we use this loss function. So the output of the discriminator with when is fed with a fake sample will be maximized, while we're gonna have the discrimination loss function, which in opposite to the generation, the output of the discriminator given the input, the sample input, the fake sample input will be minimized, while the output of the discriminator given the input, the real input, will be maximized. So now we will describe the cycle generative adversarial network proposed by Bronner. This one uses two generators in order to change the style of two domains. So if we have an input for this generator, we're gonna get the output both from the desired domain, in this case the P domain, and the discriminator as before will evaluate whether this input is real or fake. And in the opposite direction, we're gonna have another generator which will do the upside down procedure, given an input of the domain B, changing to the domain A, and with its corresponding discriminator in the same domain A. So we add into the generator a new loss function, which is the cycle consistency loss function. So given the input from the generator, we're gonna get the original input once we get the cycle procedure, and we're gonna compare it to the original sample. So if we compare the Stargardt model, which is the one that we're gonna use in this paper, in order to make the star transfer for different domains, we will have to train and test a different generator for each pair of domains. In contrast, the Stargardt will use a single generator for all the domains that we are interested to transfer. So in order to do this, we're gonna use this model. So the generator will receive not only the input, but it will condition to this C vector. This C vector, it represents the gener that we want to transfer to the input. It could be coded as a one-hot vector, and once we get the output, we send it to its corresponding discriminator. And same as before, we use the cycle consistency to achieve the original sample, given the fake sample and its original domain. Besides, we're gonna use a classifier network, which, as its name says, it classifies in which domain belongs this the corresponding samples. So these will be the training objectives for this network, for this model. First, we're gonna have the adversarial losses, which we described before. The only difference is that now we're gonna feed the one-hot vector, as we explained, which represents the domain we want to transfer the sample. And in addition, we're gonna have an identity map loss, which wanna achieve the same original sample out of the same generator, which is corresponding original domain. And the cycle loss in the same manner as we explained before, and the classification loss for the classification network, which will use this loss function. Overall, the generator, we will have all of these terms, and aside from the adversarial loss, we're gonna have this weighted loss by using these constants. So the generated network architecture is composed as is shown here. It consists in 3 stages. The downsample stage, which is fully convolutional. Actually, the whole architecture is fully convolutional, as you can see here. So we wanna achieve an encoding procedure in the downsampling of a quarter of the input, and a bottleneck, which consists in a series of residual blocks, as we can see here, and an upsampling, which we wanna have the same shape as the input using these deconvolutional layers. And these are the outputs and the size of the filters of the convolutional layers with these strides and paddings. we usually add instance normalization and rectifier linear units. And finally, we set the final layer to a sigmoid function in order to have a normalized output. For the discriminative network, we use the architecture, again a downsampling as before, with a convolutional layer and 3 hidden layers, as we can see here, and finally an output layer which is convolutional. And for the classifier network, we have this input layer. All of these are convolutional, and this output layer and a softmax, which will maintain the one-hot nature of the output. So we work in this paper with the MIDI symbolic format. MIDI stands for Musical Instrument Digital Interface, and was created as a standard communication interface between electrical instruments and computers. So as we can see in this image, the format of the MIDI is quite similar to the musical notation, and we have in these rows the pitch of the corresponding notes that are being played, and the columns represent time. So in order to create a format so we can fit the networks, we're gonna use kind of this matrix representation, which is built similarly with the rows that represent the pitch, which is which notes are being played, and along time, which are represented in the columns. And we're gonna use 3 channels which represents the instrument. In this case is drums and bass and piano instruments. Usually in MIDI there's the value of the velocity, which is proportional to the volume of the notes that are being played. But in this case, we normalize this value to 1 when it's played and 0 where it's not. So for the training, we use the Desert Camel MIDI dataset, which consists on 26,000 or so musical phrases in MIDI, and it is composed on 4 genres, which are rock, funk, bossa nova, and R&B. For the training procedure, we use the Adam optimizer, and with an initial rate of 0.302 for the generation and the discriminator, and half of it for the classifier. The constants for the weighted loss functions in the case of the cycle consistency is 10, and identity map is 5, while the class is 3. We train the model up until 30 epochs, since we didn't see any substantial improvement from there, and we taken 4 bars with 8 octaves, which as a result it represents this tensor input, which is composed of the patch size, and 64 since we use 16 notes per bar, and 84 which represents the 8 octaves, and 3 channels which represents the instruments. As we mentioned before, we normalize to the range of 0 to 1 for the volume of the notes being played, and to improve the GAN training, we use Gaussian notch for stability and to avoid overfitting, and with a standard deviation of 0.5. So first we want to show some examples of the cycle GAN, which is proposed by Bronner. As we can see here, we have the original samples, and the ones that comes next are samples that are generated by this cycle-GAN model. So by example, if we listen this, and by contrast, if we listen, just let me, so we can see that the bossa nova transfer didn't achieve musical coherence. But if we listen to the funk sample, even though it is get nearer to the domain that we are interested in, we can see that there's a disparity with the original track. And thus, for the sake of more example, if we listen this one, and its corresponding conversion to the bossa nova to rock. Which it gets nearer to the original, but it still have some disparity. Now we want to show our model results, first with the original rock track. Now, if by contrast we listen to its version to bossa nova, so if we listen, the model is able to achieve in the drums and in the arrangements of the bass pretty similar to the original bossa nova genre. If we see another example, if we hear the original bossa nova, we can see the drum sounds, it gets pretty similar for the fake one. And if we listen to the rock version of the same sample, we can see that the model is able to maintain the arrangement of the original piece, and the changes from the drums and the bass were enough to get similar to the rock genre. And only for curiosity, we can see this. Same as before, we can see that it maintains the same arrangement with the new genre. So we can mention some conclusions out of these samples, that the style transfer is achieved relatively successfully, and with the great advantage that we only use a single generator for all the domains that we are interested in. And as you could listen, the results were both musically and stylistically more convincing. We say that this is due to the different losses, especially the identity map loss, which make sure that we can achieve the same original sample using this same generator with its corresponding domain. So the future work would be expanding the dataset with broader and different styles, and using novel architectures like recently self-attention mechanisms uh, have taken the attention of the community, and also working with different formats of audio aside from the symbolic one like raw audio or some spectral representation of it. And that would be it. Hope uh, you see this as interesting, as an interesting topic. And if you have some questions, uh, down in the description I'm gonna add some links so you can contact me. And also I will add the code if you're interested in further research. Thank you.